welcome to Calculus 1. Today we're going to talk about what we so-called the related rates. Now we have used chain rules for a lot of different type of problems already. One more good usage is that the chain rule can be used to find the rate of change for two or more related variables that are changing with respect to time. So we've been taking derivative in respect to x, okay? Especially when we did implicit differentiation, where when we take a derivative of the y, where we had to use the chain rule to help us to do the derivative. Here I'm going to show you how to take a derivative, okay, in respect to time, okay. And it's actually quite simple. We're gonna take a look at this particular example. So, assuming x and y are both differentiable on a function of t, okay, find dy dt when x is 1 and given that the rate dx over dt is 2. So here's my function y, or my equation y equal to x squared plus 3. So I want to take a derivative in respect to time, okay, of y, and I'm going to take a derivative in respect to time of my x squared plus 3. So as you can see, the variable does not matching up, okay, so we have to use a chain rule. So if I take a derivative of my y in respect to time, derivative of y using chain rule, it will just be 1 times u prime, and u prime will be dy over dt, okay, according to all those formulas we have. So I'm assuming that this is my u to the first power. That's why the answer will just be 1. Alright, equal to derivative of x squared in respect to time. So derivative of u squared will just be 2u, or in our case will be 2x, times u prime. Okay, u prime will just be derivative of x over in respect to time. Alright, so a lot of time when I write dx over dt, in a way I'm telling you that I just took a derivative of x in respect to time. Okay, even though the variable doesn't match up, I can actually use the chain rule to help me to write it out like this. Plus derivative of 3 is a 0. 0 times d over dt is still going to be 0. Alright, I need to find dy over dt, and dy over dt is right here. So my dy over dt will just be 2 times, substitute 1 for x, times dx dt, which is 2. So my dy dt is going to be 4. Okay, that's the answer. Alright, let's do it slightly different. This one is finding dy over dt. Let's find one where it says dx dt. Find dx dt. Same thing. Alright, given x equal to 1 and dy over dt is negative 6. Alright, so let's take a derivative in respect to time of xy. We will take a derivative of 4 in respect to time of 4. Alright, so xy, here we're going to use a product rule. So derivative of x in respect to time, derivative of the first times the second. So derivative of x will be 1 times dx dt. Derivative of the first times the second, which is y, plus the derivative of the second in respect to time here will be 1 times dy dx, excuse me, dy dt. Alright, derivative of the second times the first. Okay, using product rule. equals this side gonna be 0. Alright, so I need to get dx dt by itself. So to get dx dt by itself, I need to move this term to the right. So 1 times x is still x. X times dy, excuse me, I need to get dx dt by itself. So dx dt is right here. So 1 times y is y dx dt. Alright, equal to, move this term to the other side will be negative. 1 times x is x times dy dt. Oops. Alright, to get dx dt by itself, I got to divide both sides by y. So my dx dt is equal to negative x times dy dt over y. Alright, so I'm going to substitute 1 for this x, negative 6 for my dy dt, but I don't have anything to substitute for y. So if you think about it, if you look back on our original equation here, if I solve for y, y will actually turn out to be 4 over x. So this y down here is actually going to be 4 over x. And the top stays the same. Alright, so now I can substitute negative x is 1, dy dt is negative 6 over 4 over x is 1. So this is going to be basically just positive 6 over 4, which is 3/2. Alright. Now we learn how to take a derivative in respect to time. It's really for the application problems. Okay. So the next 3 application problems, okay, is where we got differentiate in respect to time. This one says an air is being pumped into a spherical balloon at a rate of 4.5 cubic foot per minute. Find the rate of change of the radius when the radius is 2 feet. And this is the formula, the volume of a sphere formula. And that's the formula we're going to use. Alright, so let's think about what they're really giving me. If you think about the given here, 4.5 cubic foot per minute. Okay, the air is pumped into the balloon, so that got to be referring to the volume. So the volume in respect to time is 4.5. Okay, and the trick I use is cubic foot is referring to volume. Per time means over, per minute means per time, means over the t. So that's the given rate. What I need to find is the rate of the radius. Okay, find the rate of change of the radius when the radius is 2 feet. So that means they want me to find the rate of change of radius in respect to time when the radius is at 2 feet. Okay, because we know that as the air pumping the balloon's getting bigger and bigger and bigger. Okay, so what's the rate of change when the radius of that balloon, that sphere, is at 2 feet? Okay, what's the rate of change at that instant? Alright, so let's use our formula here. Okay, the volume is equal to 4/3 pi times radius cubed. Alright, I'm going to take a derivative. Okay, to find rate of change means I gotta find derivative in respect to time. So I'm gonna have derivative in respect to time of v, and I'm gonna take a derivative. I'm gonna pull it out. You know what? I'm gonna write it out this way. Derivative. Okay. In respect to time of 4/3 pi r to the third. Okay. All right. Using my chain rule, derivative in respect to time of v, well, would just be 1 times dv over dt equal to 4/3 pi is constant. I'm gonna pull it out. Alright, derivative of r to the third in respect to time using chain rule, that will be 3 times r squared, drop the exponent by 1, times dr dt. This problem, I need to find dr dt by rate of change of my radius. Okay, so I'm going to simplify this side right here. The 3 cancels out, so that just leaves me with 4 pi r squared. To get dr dt by itself, I got to divide both sides by 4 pi r squared. So that means my dr over dt will be this dv dt over, divide both sides by 4 pi r squared. Alright. So let's evaluate. Okay, dv over dt was given to us, the rate. Okay. Pump it. The rate of the air going to the balloon is at 4.5 cubic foot. So that's 4.5 cubic foot per minute divided by 4 times pi times radius was given us at 2 and squared. Okay, so that will be about 0.09 feet if I round 2 decimal places. Okay, per minute. Okay, so my rate of change is at 0.09 feet per minute. Alright, let's try another example. Okay, this one is about air going to a spherical balloon. This one is about a cube. All the edges of cube are expanding, okay, at the rate of 8 centimeters per second. How fast is the surface area changing? Alright, so if I expand all the edges of my cube, at the same time I'm also expanding my surface area of the cube. So how fast is the surface area changing when each edge is at 12 centimeters? So my given, alright, I'm gonna call the side, all the edges, the side. Okay. The side in respect to time, okay, is increasing at, expanding at the rate of 8 centimeters a side per second. Time is in seconds. What I need to find is how fast is surface area changing. My rate of change for the surface area. So that's derivative of the surface area in respect to time. Alright. When the edge, I call it the side, S, is 12 centimeters. Now I'm going to write this as 8 centimeters per second. Alright, so surface area. Okay, the problem is asking about how fast is the surface area changing. So surface area for a cube is 6 times s squared. So that's the formula I'm gonna use. Alright, so I'm gonna take a derivative of my surface area. So in respect to time, so that will be derivative of SA, which is, or like a U, which is be 1 du dt, or dSA over dt. Set it equal to, I'm going to pull out the 6, so take a derivative of x squared in respect to time. That will be 2s ds dt. So that'll give me 12s here. And the question is asking for dSA over dt. So that will be 6 times 2 times the side is at 12 centimeters. How fast is my surface expanding when the side is 12 centimeters and my side is expanding at a rate of 8 centimeters per second. So ds dt is 8. So that will tell me my answer is 1152 square centimeters per second. Okay. Alright. That's how fast it's changing when each edge is 12 centimeters. And I got a real interesting problem here with the radar. The radar problem is very interesting. The problem says an airplane flying at an altitude of 6 miles passes directly over a radar antenna. When the airplane is 10 miles away, let's call that s equal to 10 miles away, the radar detects the distance s is actually decreasing, because as an airplane going to an antenna here up and down, okay, this s is actually in the decreasing. Alright, so the radar detects the distance s decreasing at a rate of 400 miles per hour. What's the speed of the airplane? So the antenna is 6 miles up. Okay, my airplane is going towards my antenna, and this distance s is decreasing at 400 miles per hour. So what is the speed of the airplane? So when the airplane is 10 miles away, what is this x direction up top? And to find this x, we know the s is at 10. Okay, when the airplane 10 miles away, this x distance up top got to be square root of hypotenuse, which is 10 squared, minus my antenna, 6 squared. That will actually give me 8 miles. So this is 8 miles. And this s distance detected at 10 miles out. Okay. So what do we know? What is given? I'm actually given the rate of the airplane, or the rate of s, okay, in respect to time, decreasing at 400 miles per hour when this direction, this x direction here, is at 8 miles, horizontal direction. Alright, what is the speed of the airplane? Okay, and the speed of the airplane got to be going this way. Alright, so for my airplane, what I need to find, okay, because the airplane is not going diagonal, the airplane is going in this direction, in the x direction. So my speed got to be the ds over dt. Okay. I need to find the speed in this direction when s is at 10 and the horizontal distance is at 8. Alright, so I'm still going to use the Pythagorean theorem, okay, where s squared is equal to 6 squared plus my x up top squared. Alright, so let's take a derivative in respect to time, so that will be 2s times ds dt is equal to 36 here will become 0. Take the derivative of x squared in respect to time, that will be 2x times dx dt. So what I need to find, sorry, this is not s, sorry, s is this way. I was pointing out here and wrote s. What I need to find is dx dt. So I need to find dx dt, so I divide both sides by 2x. So my speed, okay, if you think about it, speed is actually what? How many miles per hour is how many miles going this way divided by the time. Okay, so that's why we're using the x direction. How many miles per hour in respect to time. If I divide by 2x on both sides, that would just end up to be s over t. Or 2s over 2x times ds dt. Alright, so the 2 will cancel out, so I'm not even going to write it. So the s was 10 miles out over the x direction is at 8 miles times is decreasing at a speed of 400 miles per hour. So that will give me negative 500. Okay. So that means this way I'm actually closing in at negative 500 miles per hour. So the velocity is negative 500. Therefore the speed got to be 500. My velocity is at negative 500 miles per hour. So my actual speed that traveling towards antenna is 500 miles per hour. Okay. Alright, real interesting problem. We can talk about how fast is the airplane coming towards us. Okay. Now, be careful now, the negative 400 does not necessarily mean the speed of the airplane. It actually means this distance right here from the ground to the airplane is actually decreasing at 400 miles per hour. Okay, because the airplane is coming. Okay, because the airplane is actually coming. So how fast is this dashed line is decreasing? It's going downward. It's at 400 miles per hour. So we use that idea to help us to figure out the speed of the airplane. Alright. So just a few examples on how to differentiate in respect with time. Alright, thank you.